Hi, Dr. Woeller here for Integrative Medicine Academy. I want to welcome you to this webinar. Let me close this thing out. All right, looks like we're good to go. So appreciate you joining me today. This is some advanced information called Advanced Topics in Organic Acids Test Interpretation. So if you have taken some course training through Great Plains, you're going to be familiar with the organic acid test from that company. Perhaps you've taken some courses through our Integrated Medicine Academy, and if not, that's totally fine. So I thought what I would do is go through a few things that sometimes show up on the organic acid test that can easily be overlooked or not understood. And some of this material actually comes from my Advanced OAT Mastery course. I'll talk a little bit about that later. So if this is the first time you've heard one of our webinars through Integrated Medicine Academy, we've been around as far as an academy probably for 4 or 5 years now, doing different courses in integrated medicine for healthcare practitioners. I'm also the medical director for a website called Functional Medicine Clinical Rounds, which is actually a membership site for healthcare practitioners who want to consult with us directly. And then I've been involved in education with various lab companies for clinical education, as well as just speaking all over the country and around the world on various aspects of functional and integrated medicine. In my own practice, I actually work a lot with autistic individuals, as well as patients with neurological, gastrointestinal, and autoimmune disorders. So as I mentioned, some of this material comes from our Advanced OAT Mastery course. So again, if you are familiar with the Great Plains organic acid test, you realize that this is not, it's not just a test, it's a profile. There's many sections and many markers on this test. We're not going to go through every single one, but we're going to touch on a few interesting scenarios. So first off is N-acetylcysteine. So this actually comes under the nutritional marker section of the OAT test. And this could be applied to other organic acid tests on the market. It's not common to see elevated N-acetylcysteine, but sometimes you will see elevated N-acetylcysteine, and it's important to kind of have an understanding of why that might happen. So on the Great Plains OAT, under the indicators of detoxification section, under the glutathione markers, we have 2 markers, pyroglutamic and 2-hydroxybutyric. They both have asterisk markers next to them, which means that they're indirect markers, meaning that if pyroglutamic is high, that indicates a glutathione deficiency. So in this particular case, this person's pyroglutamic is elevated, so they're deficient in glutathione. The 2-hydroxybutyric most commonly is elevated because of a glutathione deficiency, but there are a few other reasons why it could be high as well. So when we look at glutathione, here's our glutathione. It's a very complicated system biochemically in how it all comes together. But essentially what we do is we combine glutamate through something called gamma-glutamyl amino acid. And this particular enzyme called gamma-glutamyl cyclotransferase converts this to a chemical called 5-oxoproline. 5-oxoproline is pyroglutamic. So if we have an elevation of glutathione or normal glutathione, our pyroglutamic will be normal. If we happen to have low glutathione, our pyroglutamic will be high. And the main reason is that glutathione being low will often sort of force more substrate into this pathway to make up the difference. There are some genetic factors that can be linked to glutathione deficiencies as well, such as a glutathione synthase deficiency, and these tend to be more rare genetic type disorders. So glutamate comes together with cysteine to form something called gamma-glutamyl cysteine. And gamma-glutamylcysteine then combines with glycine to become glutathione. It's interesting, gamma-glutamylcysteine is the rate-limiting step in glutathione production. And this particular chemical can actually be altered by different chemicals in the body, particularly something called acetaldehyde. And acetaldehyde is a byproduct of ethanol metabolism or alcohol metabolism, but it's also a byproduct of glucose metabolism coming from candida or yeast. So it's been shown chemically that acetaldehyde can actually bind or interact with gamma-glutamylcysteine, which then could lead to a glutathione deficiency. The other marker, other than pyroglutamic, that's on that section is the 2-hydroxybutyric acid. Now, the most common reason that 2-hydroxybutyric acid could be elevated is a need for more glutathione. So the body essentially is pulling homocysteine into the transsulfuration pathway to make glutathione, and therefore we get an increased production of 2-hydroxybutyric as a reflection of that. It may be what's happening biochemically is a little bit more broad spectrum than that, which means that we could possibly see 2-hydroxybutyric elevated just because of an increased need for detoxification substrates within the liver. So glutathione being part of phase 2, bile salts being, or sulfate being part of phase 2, as well as bile salts being part of phase 3, just an increased demand to support detoxification might cause 2-hydroxybutyric to be elevated. But if you think about what's most common, it's really strongly linked to glutathione. So I mentioned before about elevated N-acetylcysteine. So under the vitamin markers of the organic acid test, there is a chemical called N-acetylcysteine. It's very uncommon to see levels that are elevated. In fact, it's most common to see N-acetylcysteine at what would be considered to be a non-detectable range. In this particular patient, we actually see N-acetylcysteine high. So you have to ask yourself the question, why would it be elevated? Well, probably the most common reason it could be high is if somebody was taking N-acetylcysteine supplementation. So if they're taking the supplement when they do the test, then the marker could be elevated. But in this scenario, what we see is we see N-acetylcysteine high. At the same time, we've got pyroglutamic and 2-hydroxybutyric elevated, which it's possible that we're not getting conversion of N-acetylcysteine to create glutathione, because we know that N-acetylcysteine is a precursor to glutathione production. So what happens is in order for N-acetylcysteine to become cysteine, it goes through a process of what's called deacetylation. Basically, this acetyl group gets removed from N-acetylcysteine to become cysteine. So when this thing is removed, okay, it becomes the amino acid cysteine, which then pairs up with glutamic acid and glycine to become glutathione. Now, there's an enzyme that is involved in removing that acetyl group called acylase 1. This is an enzyme that is zinc dependent. You oftentimes have to think about many of these converting enzymes like this themselves being potentially vulnerable to oxidative stress and free radical damage. All of these enzymes are proteins themselves. So there is a possibility that there could just be a genetic defect or something that would interfere with its function. Now, in this particular scenario, that would be quite rare. And certainly being zinc dependent, a zinc deficiency might compromise it. Fortunately, we don't see N-acetylcysteine elevated on the organic acid test all that often. but it's just important to be aware of some of the reasons of why it could be high. So low ranges actually are typical, meaning that N-acetylcysteine is adequately converting to cysteine. The person could still be glutathione deficient, but you've got good conversion to cysteine. High values could be seen in people who are actively taking N-acetylcysteine, or there is some type of poor conversion of N-acetylcysteine to cysteine for glutathione production. So let's go through a case scenario here. We have 3 different cases to kind of go through, some different things to look at. Okay, so this is a 56-year-old female, kind of typical gut issues, fatigue, headaches, brain fog. This was a little bit older organic acid test. But notice that we've got a few markers that are elevated on page 1 under the yeast and fungal section. Markers 2, 4, 5, and 6 are linked to Aspergillus mold. So this person has markers 2 and 4 elevated, which means Aspergillus is colonizing the digestive system. So we know that there's some type of exposure that's happening here. They also have high levels of arabinose linked to invasive candida, and tricarboxylic, which is actually linked to fusarium mold. And in many cases, the fusarium mold is really a food contamination. We really can't say that about the Aspergillus because it's could be food, but it's more commonly environmental. So I know I've got mold exposure happening in this individual. And that's not uncommon. So one of the tests I would be looking to do from Great Plains would be the mycotox profile. Not much to speak of about here under the bacterial or Clostridia markers. Slight elevation of 2-hydroxyphenylacetic, of a non-specific bacterial marker. So there's a little bit of dysbiosis basically. But we do have an elevation of homovanillic under the neurotransmitter section. Increased homovanillic is indicative of high dopamine. Now, a very common scenario of why homovanillic can be high is because of the presence of Clostridia bacteria. But this individual doesn't have any Clostridia bacterial toxins known to inhibit the dopamine converting enzyme. It is possible, although there is no test that I know of right now that detects for it, but Fusarium mold, the same mold that is represented by this elevation of tricarboxylic, produces a mycotoxin called fusaric acid. And fusaric acid can actually lead to elevated dopamine levels. So what are some other things that might affect this, right? It's not the Clostridia. I don't know for sure if it's, the fusarium. But, I've seen plenty of elevated tricarboxylics on the OAT and plenty of normal dopamine. So I can't say that it's 100% correlated. So remember, you can get elevated dopamine if we have some kind of block in our dopamine beta hydroxylase enzyme. Now, a copper deficiency or a vitamin C deficiency could do that. We could get elevated dopamine potentially if we're just pour in a bunch of phenylalanine or tyrosine. Although if we've got good functional status of our converting enzymes, the body should be able to compensate for that. Something that inhibits the dopamine beta hydroxylase could be Clostridia, for example. That's not happening in this particular case. So some other things that might affect it could be just genetic factors that affect the function of dopamine beta hydroxylase genetically from an activity standpoint. So dopamine beta hydroxylase is what converts dopamine to norepinephrine. It's a copper and a ascorbic acid dependent enzyme. So a deficiency of these two could compromise the function of the enzyme. I don't know how much. I don't even know if it's known how much in milligrams is needed in all cases. So again, some of these things aren't exactly known to that degree, but we know that deficiencies can cause that problem. As I mentioned, Clostridia can inhibit it. Fusaric acid from Fusarium mold can inhibit it. It may be that there are other mycotoxins because of their chemical structure, might as well. It just hasn't been proven yet. Aspartame and NutraSweet, okay, the 2-hydroxyhyperic chemical, might interfere with it too. I've seen people with very high levels of 2-hydroxyhyperic on the organic acid test being linked to aspartame, and their dopamine levels are normal. So chemically, it's possible. It just doesn't seem to be that it's a major cause. Heavy metals are suspected. Okay, so we could possibly get some interference because of mercury or lead or aluminum. Some of these markers like HVA and VMA, homovanillic acid and vanillomandilic acid, can be elevated very, very high with certain tumors. So pheochromocytoma, for example, an adrenal tumor, again, not very common, could cause some elevations. And then there's something called neuroblastoma, which is a cancer situation that occurs in kids less than 1. But again, that's not something that we're commonly seeing. So we know that interference of dopamine beta hydroxylase could occur for many reasons, and the manifestations of problems linked to it could be from anything from poor exercise tolerance to fainting spells to low blood pressure to headaches to something called POTS, postural orthostatic tachycardia syndrome. But there's many other kind of mental health and neurological conditions that could be associated with it as well. So dysautonomia is it's a very complex disorder that's linked to problems within the autonomic nervous system, with dopamine or POTS, postural orthostatic tachycardia, being a component of dysautonomia. So we have to just recognize that when we have an elevation of dopamine and we've got low levels of vanillomandilic acid on the yolk, that there's something interfering with the dopamine beta hydroxylase. Again, it could be genetic. It could be genetic plus Clostridia. It could be genetics plus a copper deficiency. So the organic acid test doesn't give us the answers for all of those questions. It certainly will give us representations of Clostridia. And if Clostridia is present and you're seeing high levels of dopamine, and the first thing you have to really go after is the Clostridia, and then repeat your test about 60 to 90 days later to see what's happened with those markers. Now, in this individual, we also have some nutritional markers. Things actually look pretty good. We've got an elevation of pantothenic acid, not uncommon. Sometimes that'll be high just because somebody's actually taking B vitamins. If you have an individual who has high pantothenic acid, for example, it could be that there is a conversion problem. So pantothenic acid gets converted to coenzyme A. Coenzyme A becomes, or complexes with things like acetyl coenzyme A to become acetyl coenzyme A. So that, but the coenzyme A is directly linked to B5. It might be a conversion block. I forget the name of the enzyme that makes the first step conversion, but there may be a genetic component to it. Usually what's suggested is to just give B5 to try to kind of override that potential blockage. You'll notice in this person, they've got high levels of pyroglutamic. Now, let me just show you something real quickly. And I don't think this is a major component, but notice this individual's NAC, N-acetylcysteine. I mentioned before that usually the levels on this test are kind of sitting down around here on the range. So it's actually kind of unusual to see an N-acetylcysteine level kind of up in that, above that first standard deviation line. If you'll notice that this individual's pyroglutamic is elevated. So there's clearly a glutathione deficiency. is it possible that we're not getting good conversion or maybe suboptimal conversion of N-acetylcysteine? And I think it certainly is a possibility. I wouldn't have a problem giving N-acetylcysteine as a supplement to help boost our glutathione levels. We do know that we've got some mold markers, so doing further testing is warranted. For example, the mycotox profile to make sure that this patient isn't having a toxicity issue from those mycotoxins. Now, another interesting scenario in this person was found on the last page of the OAT under the amino acid metabolites. And all of these markers are usually normal. So by and large, most OATs that you do, even in kids, these levels will be totally normal. So low values, by the way, where they say 0.00, have no known clinical significance. These things are only significant when elevated, and usually only significant when really elevated. All of these things can be linked to what are called inborn errors of metabolism in children. But notice we've got mandelic, phenolactic, and 4-hydroxyphenolactic acid mildly high in this person. Well, mandelic is interesting because of any marker you see on the organic acid test under the amino acid metabolites, if anything tends to show up most commonly, which isn't that common, it's mandelic. And mandelic, being is derived from acetic acid, is a known xenobiotic metabolite. So it's something that can come from chemical exposure. Whenever I see high levels of mandelic, particularly if it's by itself, I start thinking we need to look at chemical exposure. Styrene or ethylbenzene, also called phenylglyoxylic acid, can form mandelic acid or mandylate basically. So whenever you see mandelic, think it's possible this person may have some kind of styrofoam exposure, plastic exposure. It can also be from car exhaust fumes. So this is coming from the GPL tox profile from Great Plains. Now, very high levels of mandelic, typically in association with phenolactic and phenylpyruvic acid, have more to do with some kind of blockage occurring in phenylalanine metabolism. Very high levels of these things, when we start getting levels above 200 millimoles, for example, it can be linked to what's called phenylketonuria. Now that's a genetic disorder typically picked up in young children. But it is possible to get mandelic acid as a reflection of styrene exposure. It's also to have it become elevated because of phenylalanine problems or the metabolism issues linked to phenylalanine, which means that it is possible to have these things elevated in somebody actually taking phenylalanine in their supplements. Another interesting marker on the OAT under the Krebs cycle metabolites, so we've got glycolytic, Krebs cycle, and the amino acid metabolites all linked to mitochondrial function, is this marker called succinic acid. Succinic acid has a strong association with chemical exposures when it's elevated. Now, succinic acid and its enzyme succinic dehydrogenase are linked to both the Krebs cycle, right here, as well as the electron transport chain. So the Krebs cycle is connected to the electron transport chain through succinic dehydrogenase, as well as nicotinamide adenine dinucleotide hydrogen. So the NADH, for example, right here. So NADH, this complex 1 is the NADH-NAD connection, and then complex 2 is the succinic dehydrogenase connection. And one of the things to keep in mind is that all of these complexes can be altered genetically. They can also be altered by different chemical toxins and heavy metals. And if we think about the basic function of the electron transport chain, it's essentially moving electrons that carry a negative charge from one complex to the next through oxidation reduction reactions with all of these factors, CoQ10, flavine adenine dinucleotide, for example. So we're moving electrons from one complex to the next, and that movement of electrons is allowing for a proton gradient or hydrogen gradient effect, where we start to pump out positive charged hydrogens, or a proton. And in the intermitochondrial space, so if we think of this line up here as being the outer mitochondrial membrane, for example, and right here is the inner mitochondrial membrane, right? So we've got this space kind of in between. So what happens is we start pumping out a bunch of protons that start accumulating in this inner mitochondrial space. At the same time, we're moving electrons from one complex to the next. Well, eventually they start to accumulate on the outside of this ATP synthase enzyme complex. Imagine this, to me, it looks like an upside down salt shaker, right? So you're gonna twist the top in one direction and twist the bottom in the opposite direction to kind of crush the salt or pepper. So as we accumulate hydrogens, these plus charged hydrogens, we get a concentration gradient effect as well as an electrical chemical effect, because we've got high positive concentration compared to, high negative concentration. So anyway, what happens is these protons move into this upper chamber. It kind of goes through at an angle, and that causes a bit of a rotation in that upper chamber. And as these things hit that inner segment or that inner tube, whatever it's called, we've got these different oval-shaped complexes. Now, sitting in this oval shape is adenosine diphosphate and inorganic phosphate or phosphorus. So ADP and inorganic phosphate. And so as the hydrogens move through this mechanism, it causes a rotation of these oval-shaped complexes and basically takes the ADP and the inorganic phosphate and jams them together to create ATP. So that's the basic aspect of the electron transport chain. It's transporting electrons through this chain to create ATP. Anything that messes with these complexes is going to mess with ATP production. And yeah, we will produce oxidative, free radicals as a component of this, and this is why we need, good, decent amount of glutathione in our cells to help combat that oxidative stress. Phenolactic is another chemical that sometimes will show up on the last page of the OAT. It is a byproduct of phenylalanine catabolism. Now, it can be very high in children with phenylketonuria. So phenylketonuria can be a really, really problematic disease. We know that biochemically, phenylalanine gets converted to tyrosine. Tyrosine is converted to L-DOPA to help us make dopamine. It's converted to CoQ10. It has a role in thyroid. It also helps with melanin production. If we have a block of our phenylalanine hydroxylase, so right here, this would be phenylalanine hydroxylase. That's that enzyme that converts phenylalanine to tyrosine. It's actually dependent on a chemical called BH4, tetrahydrobiopterin. And tetrahydrobiopterin itself is recycled through the actions of nicotinamide adenine dinucleotide. It's actually, more specifically, nicotinamide adenine dinucleotide phosphorus, but basically it's recycled because of these complexes. And so in kids with phenylketonuria, they figured that they've got some kind of major deficiency in BH4. And there's actually medications that you can take to replenish BH4. And BH4 is a cofactor that makes that phenylalanine hydroxylase work effectively to convert phenylalanine to tyrosine. If it's blocked, then we get a buildup of phenylalanine as well as different organic acids. So on the organic acid test from Great Plains, we've got phenylpyruvic and phenylactic. Other companies may have phenylacetic acid as a reflection of this. But we could also have interference of this enzyme. At the same time, through dietary protein or endogenous protein feeding into that phenylalanine system, that too could cause increases of these acids. It turns out that ochratoxin from Aspergillus is a phenylalanine hydroxylase inhibitor. And it's likely other fungal compounds will do it too. Now, in phenylketonuria, many of these kids have early on neurological problems, mental retardation, seizures, microcephaly, they get hypopigmentation. Remember, tyrosine is involved in melanin production. They have poor catecholamine production, so low dopamine, oftentimes low norepinephrine. They've got mitochondrial deficits. A lot of times that musty odor smell will appear. Now, 4-hydroxyphenolactic was another chemical that was showed up on this individual. And this is a little bit more complex, but if we just sort of follow it out, there's all kinds of things called disorders called tyrosinemias. So phenylalanine gets converted to tyrosine through the actions of phenylalanine hydroxylase. Right? So we already know that if we have deficiencies in tetrahydrobiopterin or something that's interfering with phenylalanine hydroxylase, that could cause our phenylalanine to build up. There are some very serious, fortunately rare genetic disorders like tyrosinemia 1, tyrosinemia 2, tyrosinemia 3 that can appear sometimes in kids. Alkaptonuria is a rare disorder, although it tends to manifest in older individuals, 30s and 40s. And what ends up happening with these people is they get dark pigmentation that will get into their skin, get into their gums, and then it has a toxic effect on the brain and nervous system. Again, because of some type of genetic defect in some of these converting enzymes. But this particular chemical called 4-hydroxyphenolactic acid, also called para-hydroxyphenolactic acid, can be linked to a defect in our para or 4-hydroxyphenylpyruvate dehydrogenase enzyme. Now, you might ask the question, well, how is this pyruvate deoxygenase linked to lactic acid? Well, if you remember the basics of glucose metabolism, right? We produce pyruvic acid. Pyruvic acid gets converted to acetyl coenzyme A. If we can't make that conversion, we can also produce lactic acid as a byproduct of anaerobic metabolism. In this particular case, Great Plains is using the lactic acid, okay, as a metabolite of a defect in this enzyme. And that's basically a blockage here. So a blockage at 4-hydroxyphenylpyruvate dehydrogenase will cause the 4-hydroxyphenylpyruvic acid to build up, and it can spill over as either a phenolactic or a phenylacetic. I don't know for sure. I know that some of these organic acids are relatively unstable in urine samples, and it may be that's why they went with the lactic acid, for example. So here's where it gets kind of interesting just from a more broad spectrum thing of what I had mentioned before. Remember, this person had high levels of Aspergillus markers on the OAT. They also had high levels of tricarboxylic as well as Candida, which is a yeast, right? So This was an article came out a number of years ago, back in 2010. And one of the things they talked about was that tartaric, now this is an older article, they were specifically linking tartaric to yeast and candida. But remember, the biological group of organisms is fungi, right? So mold, including Aspergillus, penicillium, etc., are fungi. Yeast, which would include candida, is also a fungi. But candida is not a mold and Aspergillus is not a yeast, but they're all fungus. So tartaric acid is now looked upon on the organic acid test having a strong association with Aspergillus mold. But tartaric acid, and I already mentioned that ochratoxin, which is a mycotoxin of Aspergillus, tend to interfere with phenylalanine metabolism. In fact, what this article also talked about was tartaric acid contributing to tyrosinemias. So, and we've got phenylketonuria. So we can not only have maybe interference in the tyrosine pathways, but also interference in the phenylalanine pathways secondary to some of these fungal organisms. Okay, so that was just one thing I wanted to go through. Let's go through case scenario 2. So this is a 3-year-old autistic individual. And like a lot of these kids, he's got some yeast issues. So we've got a high level of arabinose linked to invasive candida. And we have another Aspergillus marker, the furan carbonyl glycine. Now, of all of the 4 Aspergillus markers on the OAT, furan carbonyl glycine is the one seen least commonly, so it doesn't show up that often. And it can be a little confusing when you look at this with regards to what can be linked to it. It is an Aspergillus marker. It's also sometimes talked about being a metabolite of Saccharomyces cerevisiae, so that could be something linked to brewer's yeast or baker's yeast. Now, this particular child's got some other stuff going on. We do have some markers in the bacterial section, as well as one Clostridia marker. And if you've heard me speak before, we know that the HPHPA is the most common Clostridia marker to show up on the organic acid test. So about 1 in 5, maybe 1 in 4 organic acid tests that you'll do will have at least one Clostridia marker, HPHPA being most common. And what these toxins do, HPHPA and 4-creosol, for example, is they inhibit the dopamine beta hydroxylase, which inhibits dopamine conversion to norepinephrine. And that can cause our dopamine to elevate, which would then be registered as an increased homovinylic acid on the organic acid test. But notice that this child's homovinylic acid is not high. And that will happen in some cases. And so I often in practice will use what I call the 80-20 rule. And that is 80% of the time when a Clostridia marker is present, you're going to see an elevation of homovinylic acid. But about 20% of the time you won't. It's not to say that it couldn't happen. Every test we do is a snapshot in time. So if I were to just leave things alone and not go after the Clostridia, then likely down the road, we're going to eventually get enough inhibition on that dopamine beta hydroxylase that the dopamine would become elevated. Now things get very interesting when we turn the page to the oxalates and the mitochondrial markers. There's all kinds of stuff going on here. Clearly there's an oxalate issue, and we're gonna not really talk about that here. That would be a whole other discussion. But Aspergillus mold can produce oxalate, so can Candida, and then of course we get oxalates from diet. It's likely in this particular child we've got some kind of genetic component as well, with the glycolic and the glyceric levels being high. I know that oxalates can interfere with mitochondrial function. So I know that that's one thing that could contribute to all, some or all of these markers in these sections below it. So can mold, So can Clostridia, so can Candida. It's not uncommon to see high levels of lactic acid because of mycotoxins. There are other reasons for lactic acid elevations. So a thiamine deficiency could lead to that problem. Succinic has a strong association with chemical and heavy metal exposure. So when I see a test like this, I already know that I want to check for mycotoxins. But when I've got high levels of succinic, for example, I'm going to be thinking chemical and heavy metal exposure as well. We could dive into every single one of these markers, and we actually do in our advanced OAT course, and really pick these apart. But basically, we've got some mitochondrial issues happening here, likely secondary to other factors: oxalates, mold, candida, Clostridia, probably some nutritional deficiencies, chemical exposure, heavy metal exposure. Now, this kid also has a folate problem. It's probably a either folate deficiency issue in the diet or some type of folate transportation problem where it can't get into the cells. It's actually uncommon to see a uracil this elevated. So these things are actually linked to folate metabolism. The ketone fatty acid section has a strong link to the mitochondrial markers. Okay, all of these are relatively about the same level, so nothing really is standing out, exceptionally really high. Some of this could come about because of an L-carnitine problem. L-carnitine deficiencies are more common than you think, and that can contribute itself to mitochondrial issues. Now, when we look at the uracil, the pyrimidines real quickly, these are these chemicals that are involved in RNA and DNA. So the pyrimidines are cytosine, thymine, and uracil, and the OAT picks uracil and thymine as representations of folate metabolism problems, primarily because thymine is linked to DNA, uracil is linked to RNA. It's very common to see high levels of uracil more so than thymine, probably because there's just more activity within the RNA system with regards to translation, transcription of the DNA for protein formation. Now, another aspect of this, as you'll see, is the ability to support mitochondria, right? We know that there is a mitochondrial issue happening here, and probably multiple things affecting it. And that folate deficiencies, right? This child has a folate problem. So if we have a folate deficiency issue, we're not able to methylate cobalamin that's sitting within our methionine synthase enzymes adequately. And then that can lead to, energy problems, that can lead to detoxification issues, etc. It's interesting in that we need ATP in order to produce SAMe, S-adenosylmethionine, which is one of the major methyl donors in the body. So in order to get homocysteine to methionine, we need actions of methylcobalamin through activity of our methionine synthase enzyme. And in order to methylate cobalamin, we need active folate. So this child's got poor folate, so they likely have low levels of active folate, which could compromise downstream their ability to make SAMe and make our methylation cycle move. One of the other things that happens in chronic exposures to toxins is that the methionine synthase enzyme itself is very sensitive to oxidative stress and inflammation. Well, if we look back on the OAT, we can see we've got mold, we've got candida, clostridia, oxalates. All of those things can generate oxidative stress. One of the other things that's happening in this individual is a high level of methylmalonic acid. Methylmalonic acid is linked to a B12 deficiency. We also have a riboflavin deficiency. And riboflavin is very complex as far as where it is active within our body and within the cell. Riboflavin is actually needed by MTHFR in order to help convert inactive folate to folate. Riboflavin is needed in various enzyme complexes that are involved in glucose metabolism through pyruvate dehydrogenase. It's active within the Krebs cycle through an enzyme called alpha-ketobutyrate acid. It's also involved in amino acid metabolism that itself, if deficient, could lead to mitochondrial deficits. So we've got a problem here in riboflavin. It's not uncommon to also see elevations of glutaric acid linked to a riboflavin deficiency because of chronic fungal problems, particularly yeast and candida. And what happens is that I mentioned earlier a chemical called acetaldehyde. Candida will convert glucose to an end product, ethanol. But the biochemical step before that happens is an acetaldehyde chemical. And aldehyde chemicals by nature, which chemically carry a carbon, a double bonded oxygen to a hydrogen, are highly reactive functional groups on chemical compounds. And so our body has all of these different systems. In fact, many of the P450 systems that are part of phase 1 detoxification are there to help basically, get rid of these aldehydes. It either converts things to carboxylic acids, which is a double bonded oxygen to a hydroxyl group, or it converts things to alcohols, whatever it may be, but the body wants to get rid of these aldehydes. And there's exogenous aldehydes that we come in contact with too, chemicals, for example. So it's not uncommon to see elevations of glutaric, meaning a B2 deficiency when there is a lot of candida. All right, so methylmalonic acid is linked to B12 status. Methylmalonic acid is elevated when we can't convert something called methylmalonyl coenzyme A to succinyl coenzyme A. Succinyl coenzyme A is another entry point into the Krebs cycle. So let me show that to you real quick. So if we think about our methylation cycle, right, we tend to hyper-focus on MTHFR, and sometimes people forget that this methionine synthase enzyme is a big deal too, because it's directly involved in converting homocysteine to methionine. Cobalamin gets methylated by methylfolate to become methylcobalamin. But cobalamin can also pair up with adenosyl to become adenosylcobalamin. And adenosylcobalamin is what converts L-methylmalonyl coenzyme A to succinyl coenzyme A. Succinyl coenzyme A then feeds into the Krebs cycle. If this gets blocked, we get an increase of methylmalonic acid, and that's called methylmalonic aciduria. So downstream, this could be another reason why we have mitochondrial problems in a child like this. So here is our succinyl coenzyme A entry point. So if you keep in mind, there's multiple areas to get into our Krebs cycle. And if you sort of think about just metabolism from a broad perspective, proteins, fats, and carbohydrates. Now, carbohydrates and fats, right? We basically break down carbohydrates or convert it to help produce energy, and then we can store it as glycogen. Fats certainly play a big role, but we get a lot of metabolic activity or bang for our buck by burning fats. Protein, a lot of people think that protein, plays a primary role in energy production. And it does, but the primary reason for protein is really to restore protein stores within our body. And then, of course, we can use it to also make energy. So we enter the Krebs cycle through this pathway up here, okay, which is going to be pyruvate to acetyl coenzyme A, okay, right at the entry point of oxaloacetic acid to citrate, under the actions of citrate synthase. But we can also enter at succinyl coenzyme A, which is back-linked to B12. So, and then of course, succinic dehydrogenase and our NADH go off to the electron transport chain. Now, notice we also have in this kid high levels of pyroglutamic and 2-hydroxybutyric. So most likely the reason for these elevated markers is because of all of the toxins that are going on. Mold, oxalates, candida, probably some chemicals, although we'd have to test for it, probably some heavy metals, although we'd have to test for it. But there's enough off the organic acid test to just show us why this individual would be deficient in glutathione. This 2-hydroxyhyperic that's elevated right here at that level, that could be from intestinal bacteria, probably not. It's probably just from food. It could be from NutraSweet, artificial colors, or artificial flavors. Okay, so finally, the last scenario. So this is a 74-year-old individual, kind of typical chronic fatigue issues, a poor diet, metabolic disorder, etc. In fact, diabetic, I believe. One quick thing, by the way, and that is, well, first off, we've got a few things happening here from a yeast standpoint, right? We've got high levels of arabinose, so we know candida. We've got high levels of tricarboxylic, so we've got fusarium mold, and then 3-oxaloglutaric. So as I mentioned before, 2, 4, 5, and 6 are linked to aspergillus colonization in the gut. And the reason they know that is that there was a paper that was done where they looked at these organic acid markers before and after in a group of individuals where they were given nystatin. And so nystatin is a non-systemically absorbed antifungal, and so it's only going to have effects of things within the digestive tract. It doesn't get absorbed and have systemic effects throughout the body, like diflucan or Sporanox could be. It's certainly possible in somebody who has these elevated markers on their OAT, it's possible they could have aspergillus somewhere else. It could be in their lungs, it could be in their sinuses, for example. It's not to sit there and say it's only in their gut. What the organic acid test is telling us, though, is that most likely, you know, again, because of colonization within the gut, we at least know that some of it is there. You'd have to do, you know, additional kind of testing to see if it's elsewhere, for example. Not much to speak about under the bacterial and Clostridia markers. Okay, a little bit of, you know, 4-hydroxybenzoic, but again, kind of non-specific bacterial marker. But we got a ton of stuff happening under the mitochondrial section. In fact, almost every marker on this page is elevated. We certainly know that oxalates could contribute problems to the mitochondrial issues. Lactic, succinic, mitochondrial issues, again, mold, candida, mycotoxins, heavy metals, chemicals could certainly be some significant contributing factors. We do have elevations of homovinylic acid, okay? In fact, did we have, no, we didn't have any elevated Clostridia markers, so it's not likely these are coming from Clostridia, they're coming from something else, right? Perhaps there is a mycotoxin interference. Perhaps there's a copper deficiency or some need for additional vitamin C, or there may be a genetic component here as well. I don't have a lot of time to talk about this marker here, but quinolinic is something to watch out for. Elevations of quinolinic are neurotoxic. It's basically an NMDA receptor stimulator in the brain or nervous system. which can cause toxic reactions within the brain and nervous system. It tends to be high or get generated in scenarios where there's a lot of toxic stress as well as chronic infections. But here's what I really wanted to show you. Under the fatty acid ketone fatty acid oxidation section, we have these different markers that are linked to fatty acid metabolism. Some of these are, when they're very, very elevated, are quite rare from a genetic standpoint. But it's not uncommon to see some markers elevated in this part of the test. This is one part of the test that can be influenced by diet. So somebody doing a ketogenic diet, somebody eating really high fat food or using medium chain triglyceride oil, for example, could inflate these numbers. Typically, when somebody's using MCT oil or coconut oil for cooking, you'll see elevations of all of these markers, but they're all relatively at about the same level. The first two, 3-hydroxybutyric and acetoacetic, are ketogenic acids. And notice how much higher they are than everything else, okay? They're extremely elevated while everything else is just slightly elevated. And so branched chain amino acid, valine, leucine, isoleucine, okay, can be part of these ketogenic acid productions, as well as certain fatty acid breakdown that oftentimes gets generated through a ketogenic diet. But we produce acetone, acetoacetic, and then something called beta-hydroxybutyric acid. So in a ketogenic or ketosis, I should say, type of scenario, right? Free fatty acid, we can get either from amino acid, these branched chain amino acids. This one is just looking specifically at isoleucine, but it could be free fatty acids that break down. And in this particular case, they sequence all the way down to HMG coenzyme A to become acetoacetic acid, being converted to 3-hydroxybutyric acid. And those keto acids then go off into other tissues of the body, including the brain, to be used as a fuel source. If you look at this individual, we have, this person's also B12 deficient, so they got a B12 deficiency. We've got a high pantothenic acid that could just be a conversion problem. We have high levels of 3-hydroxy-3-methylglutaric, which is linked to CoQ10, right? So we've got a CoQ10 deficiency, which could contribute to some of the mitochondrial problems. Now notice that this individual's N-acetylcysteine is at 0, which I mentioned before means that there should be good conversion to cysteine. Okay, so that acylase enzyme should be working. 2-hydroxybutyric. Okay, our 2-hydroxybutyric is elevated, but notice that it's elevated by itself. Our pyroglutamic is normal, and this elevation is quite significant. Okay, most of the time with 2-hydroxybutyric, when you see it on the OAT, you're looking at a level of 2.2, 2.4, 2.8, maybe in the 3s, for example. It's pretty unusual to see it this elevated. Well, it turns out that 2-hydroxybutyric is also, remember, it is a marker that could be linked to glutathione production, but it can also be an early marker for insulin resistance and impaired glucose regulation. So it's often elevated in people in ketosis, okay, or ketoacidosis. In fact, there was an article that looked at 2-hydroxybutyric in reference to impaired glucose tolerance, actually in some cases being even more sensitive than things like hemoglobin A1C. So it is a sensitive marker to glucose dysregulation. Now, it is marker 59 on the OAT. In this paper, they also looked at oleic acid. oleic acid is linked to subearic acid on the organic acid test. So if we go back to this individual who has a metabolic disorder with regards to glucose and insulin issues, we've got high ketogenic acids, and we can see a high subearic acid that is linked to oleic acid. Oleic acid is the main form of fat that's stored in our adipose tissue, right? So we're basically have a patient that is in a ketosis type of scenario. If you pick up on something like this, you know, it's worth doing blood testing on this kind of individual, looking at serum glucose, fasting insulin, hemoglobin A1C, for example. So we actually have a couple courses through our Integrative Medicine Academy. We have the Essential OAT Mastery course, which is about the fundamentals of interpreting the organic acid test and really looking at the more common markers that you'll see show up, and then starting to understand how different sections of the OAT compare to themselves, like how does the fatty acid metabolite section link up to those mitochondrial sections. The Advanced OAT Mastery course is going into each and every marker in a very in-depth way. The material I talked about here, I actually pulled from a few of the lectures that are in the Advanced OAT Mastery course. If you need some, you know, fundamental or introductory experience with the OAT, then it's strongly recommended to take the Essential OAT Mastery course. If you have gone through that and you feel comfortable for the most part with some of the basic information about the OAT, then the Advanced OAT Mastery course is the natural place to go. It's a very, one of the most in-depth courses that we have through our Integrative Medicine Academy. And so we actually have a course coming up in a few weeks. So for more information about the Advanced OAT Mastery course, go to advancedoatmasterycourse.com. Now, we also have another website called Functional Medicine Clinical Rounds. This is a membership site. This is not a course. This is an ongoing membership site where healthcare practitioners can get access to ongoing educational material. So we have new videos that come out a couple times a month. We've got once a month live clinical rounds where we do a webinar through that with ongoing questions and answers. We have an interactive member forum. And you can also schedule one-on-one consults with myself and my partner, Dr. Tricatella, for lab reviews. That could be reviewing an OAT test, that could be reviewing a mycotox profile, as well as other companies' lab tests. So it's not just Great Plains testing. Okay, and so through the site, you can book a consult with us. Again, there's a whole library of videos, interactive forum for ongoing questions. And then once a month, we have kind of a short lecture with just a live Q&A session. And then we also have this really cool section called Clinical Rounds Data Sheets. These are all downloadable documents, one-page PDFs that get produced weekly that are on lab interpretations or just clinical pearls from practice. This could be mycotoxin, hair metals, hormone testing. There's a whole slew of these things that are added once a week that all come in downloadable PDFs. So this is also found within the website. And if you have any additional questions about Integrative Medicine Academy, our different courses, from the OAT courses to our functional medicine to our toxicity course, autism, whatever it may be, you can reach out to us through the Integrative Medicine Academy at gmail.com. And then the main website is integrativemedicineacademy.com that has an overview of all of our courses. Thanks so much, everybody, for your attention today. I hope you found this information interesting. I'm Dr. Woeller for Integrative Medicine Academy. Thanks so much. Take care.